The subject of this video is R value. If we have a wall blocking the inside from the outside, and the inside is warmer than the outside, heat will flow from the inside to the outside. Now heat will flow due to convection from the air inside onto the surface of the wall, and then through the wall due to conduction, and then from the wall to the outside due to convection. So each of these terms has an R value, or a resistance to heat flow. Now the resistance is the inverse of the conductivity, because if we increase the conductivity, we make it easier for heat to flow, meaning there's less resistance. And if we decrease the conductivity, we make it harder for heat to flow, meaning the resistance has increased. So R value is a unit of resistance. In fact, it's the resistance per unit area. So in order to find out how much heat is flowing, we multiply area times the difference in temperature, and then divide by the R value. Now this is a useful property because we can take the R value of each term, for example the convection term, the conduction term, and the other convection term. We have two convection terms, one for the inside and one for the outside, and add them all together to get a total, because each R value adds together to create one total R value. Let's do an example to understand how R value is applied to heat transfer. Looking at the surfaces first, we see that heat flows due to convection. And on the inside for this example, the heat transfer coefficient is 5 watts per meter squared, and the temperature inside is 20 degrees Celsius. And on the outside, we use a heat transfer coefficient of 15 because breezes on the outside will increase the heat transfer coefficient, even though inside and outside has the same fluid air. Now the outside temperature is 0 degrees, or 20 degrees difference between the inside and the outside. And for the wall, we have a conductivity of 0.15, which is roughly the conductivity of wood, and we have a wall thickness of 0.1 meters, or 10 centimeters. Also, the area of the wall we're looking at for this example is 20 meters squared. Now we're going to use these terms to find R value and the total heat flow through the wall. However, after that, we can also find the surface temperature on the inside of the wall and on the outside of the wall. The surface temperature on the inside of the wall is not the same as the temperature of the air on the inside, and the surface temperature on the outside of the wall is not the same as the air temperature on the outside. So first we find the R value of each term. Going back to our equation, we see that R value for convection is 1 over H. So for the inside, we find that the R value is 1 over 5. Now for the wall, we use L over K, or length over conductivity, and the thickness of the wall is the length. So we divide 0.1 by 0.15 and get that the R value of the wall is 2/3. Then the heat transfer coefficient for the outside is 15. So to get the R value for the outside, we divide 1 over 15. Then we add all these R values together to get one total R value, which comes out to 0.933. We simply multiply the change in temperature times the area and divide by the R value. And since the total R value is 0.933 and the change in temperature is 20 degrees Celsius and the area is 20 meters squared, we multiply 20 times 20 and divide by 0.933 to get 428.7 watts of heat flowing through the wall. This is a very useful term in the real world because determining how much heat is flowing through the walls of a building determines how much heat is needed to put into the building to maintain the difference in temperature. Now that we know how much heat is traveling through the wall, we can determine the temperature of the surfaces. Let's look at the inside surface first. Since we know that the heat transfer coefficient times the surface area times the change in temperature equals the total amount of heat traveling into the wall from the air, and since we know that the heat transfer coefficient is 5 watts per meter squared Kelvin, and the area is 20 meters squared, we can solve for the change in temperature by dividing 428.7 by 5 and by 20. And this means the change in temperature is 4.29 degrees. Now we know that the wall is colder than the air inside because heat is leaving the inside. So we subtract 20 by 4.29 to get a surface temperature on the inside wall of 15.71 degrees Celsius. We use this same method to determine the surface temperature of the outside wall. Since we know that 428.7 watts of heat is coming off the wall, we can divide 428.7 by 20, the surface area of the wall, and by 15, the heat transfer coefficient on the outside. We then get a difference of temperature between the outside wall surface and the outside temperature of 1.43 degrees Celsius. This means we know the surface temperature of the wall is simply 0 plus 1.43 degrees Celsius, or 1.43 degrees Celsius. And so our final answers are that 428.7 watts of heat are flowing out of the wall, and that the inside surface temperature is 15.71 degrees Celsius, and the outside surface temperature is 1.43 degrees Celsius.